Do we do this in English or?
Yes, in English.
Okay. All right, we'll do this in English, I suppose. My name is Alex Weibel. Who knows me, actually? Oh, that generations change quickly. Who does not know me? Okay. I started this lecture actually in 1991 when people didn't do neural networks. And when I came as a professor here to Karlsruhe, we developed a program over the years with neural network learning for various applications, and we built lots of systems like the lecture translator and many companies, etc. And I will tell you a little bit about this. So today I'm your guest lecturer. As of this year, for the first time, I'm not giving this lecture. Jan Nihus and his team are doing it now. And that gives me more chance to actually work on some research projects that have been dear to me, more time, and also on the other projects that I have at Carnegie Mellon. I'm a professor at 2 locations, at Carnegie Mellon University in the US and here at the Karlsruhe Institute of Technology. And for many years, I've been going back and forth to do research and teaching in both of these places. Many of the professors here actually came from our lab. Jan Nihus did his PhD here. Rainer Stiefelhagen did his PhD in our lab. And Kai Rottmann, who you heard, he did his PhD also in our lab. So many people grew out of this activity here at Karlsruhe and also in collaboration with Carnegie Mellon. We have a exchange program that I want to mention. This is something we've run for many, many years, where students have a chance to also do in this exchange. And this, as I said, many of these famous scientists now have grown out of this exchange program, where they spend some time either at Carnegie Mellon or one of the other partner universities that we collaborate with. So there are 8 universities in the network of Interact. Interact stands for International Center for Advanced Research Communication. Advanced, oops, what happens here? International Center for Advanced Communication Technologies. And what we've done over the time, we've actually worked together with, why is it not switching? Huh. Yeah. So, and we built a network of these universities so that students have a chance to go to another well-known university around the world and do some research projects in collaboration with other scientists. So every year or every semester, actually, we have a selection process. Margit Röder is responsible for that here in our building. So if you're interested, please create an application so that you may have a chance to potentially do a research project in exchange with one of these partner universities. As I said, I'm a professor at Carnegie Mellon University, so I spend more time there now nowadays to build up a new program that we're doing there, and I'll tell you a little bit more about that as we go. So here's a little review. We had lots of students, more than 200 students who've gone to through Interact to Carnegie Mellon or to Japan or to various other countries and places to do their research project, and that has been very beneficial for doing something interesting in collaboration with well-known scientists. Before also start, today's lecture is supposed to be on history. So I get to basically tell you stories from the many years of work that we've done. Carnegie Mellon, as you know, is one of the leading universities in AI in the United States, probably has the rank #1 in the US. And at Karlsruhe University, we were the first to do an AI conference in the 80s already. And so there is an illustrious history here and there, and the combination, of course, has been very productive. Now, how do we use, so I want to start in an overview today about how we approach science, then tell you a little bit about the practical systems that we built, and then get into the fundamental research we've done on neural networks and connect the two so that you get an idea how we see science in general. In general, technology disruption is a word that is hard to translate. In fact, there is an institute in Germany for Sprunginnovation, which means jump innovation, which is supposed to be like disruption, but it misses a critical point, namely that as soon as you have a new technology coming around, it destroys something that is already in existence, and that tends to be painful. And so disruption is a process that is generally encouraged more in the United States. In Europe, we tend to be more cautious, and as such, disruption is one of those words that every society struggles with. Now, that said, how does it happen? Usually when we talk about technologies, we start with something that is like a crazy idea, where we look at fundamental research, some idea, some vision that we may have, but it's really far out and it's not particularly practical. And so few people actually work on it. So if you look at the resources devoted to a task versus the applicability of the product closeness, then usually when you're down there, you might be the first picoseconds of the universe. It's interesting, but few people really work on it. And once you really take a crazy idea and move it in the realm of something productive that is actually useful, then you see this is actually working. And then suddenly there is a jump into industry and exploitation, and things take off. So in this transition, of course, so when you have this transition from something that's a crazy idea to something where you can really see the usability of it, that's a very, very interesting part to be, a point to be, because we see the impact of the work that we do, and we see how it actually transfers into society. Now, that's where we see our role really here in Karlsruhe, as well as at Carnegie Mellon. We want to do research that is motivated by a practical, important goal, and then we see how this, and if it's really too hard, too crazy, then we really need to do fundamental research to make it viable. And so that fundamental research is university research, and that's why we do it here. What do we do when it really becomes practical, when it really starts working? Then we have this process of transition. And transition generally, and very often at university, means we give it to a company, and the company somehow is happily taking it on and doing it. But in general, that doesn't really work that way either. Usually when an idea becomes viable, it's still not mature enough so that it really feeds into a large company that can run with it. And very often there's a role for startup companies to do it, to take the risk of the new technology and really move it to something where really first products come out. And you see this time and again in many industries, and I can give you many examples that we built, but you see this in all the things that you see in the news, neural networks, OpenAI, all of these companies, Google, Apple. When I started with my research, there was no Apple, there was no Google, there was no Microsoft. Was actually, while I was a student, there was another student called Bill Gates who was just down the road. I was at MIT and he was studying at Harvard. And so these were crazy times where nobody really thought these things would be viable until some small company did it and really proved that they could begin building a large industry, which then dominated the world. We still see this today in front of your eyes. You see all these adventures happening as we go. OpenAI is the latest one, but it's not the first one. We had many of that like that before. So this is exciting because, you know, when startup companies succeed, they either take off in their own right by IPOs and so on, or they become acquired and turn into companies with other large companies, merged with other large companies. So what I want to talk about in the time that I have with you here is to give you a bit of a vision of a practical systems that I've been engaged in. That's been the vision for my career, which is to break the language barriers. And it's something that we already more or less achieved. Then we'll talk about the neural network science and the systems behind it, how we really started with very primitive neural networks all the way to machine translation and language transparency. And then I will give you a bit of a view for where I see the future is going, where further research is needed in AI, and where interesting, new, exciting topics actually emerge. Now, to start with these practical visions, this is something that I started with in the, well, I was a student at MIT in the 70s. 1976, I started my studies at MIT. And in those days, there was no Apple, there was no Google, there was no iPhone, there was no Microsoft, there was no, in those days, I wrote letters to my mother on paper and pen, and we folded it into something called an envelope. And then we put something called a stamp on it. And then we carried the letter to the mailbox and we dropped it in the mailbox. And 2 weeks later, maybe you got a response from mom. And it took a long time. There was no email. In fact, in our lab, we had an interesting, at MIT, there was a neighbor lab which was working on VLSI chips. So they were creating the first course on VLSI design. And this VLSI design had to be manufactured in Silicon Valley, and MIT being on the East Coast, there were communication problems. So they put along with the design, so DARPA at the time invented the DARPANet, which then later became the internet. And so Bob Kahn and Vint Cerf, two gentlemen that I know personally, who are very interesting icons, they developed the internet protocol. Which one? Did you have a question?
Was it not developed in the Swiss, the internet?
No. This was the World Wide Web that came later, much later. But the internet protocol, and there's a joke. I was expecting you to say wasn't invented by Al Gore, but you guys are too young to maybe remember that Al Gore was in his presidential bid claimed to have been involved in it. But it's the true story is that Vint Cerf and Bob Kahn were DARPA managers at the time, and DARPA decided we needed to have some communication channel where we can send data from one part of the country to the other in the United States. So they set up this protocol with which you could do that. Now, at the time, when you send chip designs from one part of the country to another, you need to have some explanation. So people developed little README files that they would send along, and lo and behold, these README files turned into email. And so people would send email to each other from one part of the country to the other. And so this was the start of email and the start of the internet, and it just happened just in these labs around us for practical reasons. Later, when I was at Carnegie Mellon as a graduate student, interesting little side story, there was a debate over email about some guy was mentioning something about mercury in the elevator, and everybody panicked, and he said, "Oh, that was just a joke, guys, I didn't mean it, And so one of my colleagues, we shared an office for a while, Scott Farman, he said, "Okay, I propose that in the future, if you make a joke, to make it clear that it was a joke, you should put colon, minus sign, close parentheses." And that was so funny that this was sent to Stanford and to Berkeley and to MIT, and those geek schools, those 4 leading computer science schools, started using the first emoji in history. This is actually proven. There was a forensic research of old Mac tapes to find that old email where that was actually suggested, and it is really true, traceable back to Scott Farman as the inventor of the emoji. And so he's now, he always privately jokes that, he was always wishing to be famous for his research, but in his whole career, he only became famous for the famous emoji. Now, my vision in all of this was really language, because I was at MIT in a project that was for the first time building speech synthesis. And the idea of speech synthesis means you put text in and it speaks it out. In 1976, that was a crazy idea, talking machines that seemed almost freakishly science fiction, that it was something very innovative and interesting to do. And so I was part of a project that was building a first reading machine for the blind, and a company in California came from that, and they manufactured a board which did an automatic text-to-speech synthesis. In 1978, I was working with this company as a student in 1988, and one of the early customers of that board was Stephen Hawkins, and Stephen Hawkins had that board in his wheelchair. And since the voice was designed after one of the colleagues at MIT, Dennis Klatt, that's also a sad story, actually. Dennis Klatt designed the synthetic voice after his own speech. And so it sounded like him. This text-to-speech system sounded like Dennis Klatt. And so when it became a product, the voice that resulted really sounded like him. Now, Dennis Klatt developed laryngeal cancer. So he had cancer in his larynx, and that caused him to lose his voice over time. And it was sad when he then would come to conferences that he brought his synthesis machine and let the synthesis machine deliver his paper. It's sad in a way because it's almost spooky, like he gave his voice to the machine and the machine lived on. Now, the voice of his machine lived on in the voice of Stephen Hawkins because it was developed after him. And if I hear speeches today recorded by Stephen Hawkins, I still hear Dennis Klatt as the originator of that voice. For me, in these days, synthesis wasn't the ultimate goal. I grew up in Europe and I was confronted with many languages. So to me, it was always a desire, how do we connect people talking different languages? There are 7,000 languages in the world. Right here, you guys probably speak at least 3 or 4 if I look around the room. And so as you know, if you're not familiar with German, for example, you come from a foreign country, you struggle with language. You struggle with the fact, how do I communicate with German people? They're culturally different, but they're also language different, and to understand how they speak, etc., is a challenge. And now for us to deliver the language, this lecture in English, in a German university is also a bit crazy because every country has their own language. It should be proud of their own language. And how do we connect people if they speak different languages and can't understand each other? Now, the problem is enormous. It's not just the 23 languages of Europe, but if you go around the world, there's actually 7,000 of them. And to connect everyone is no longer a technical problem with the internet and with communication channels, but it's today a language problem because we don't have a translation technology in all of these languages. Now, back in the 70s, this was a dream. It was impossible to do. In the 60s, there was a report by ALPAC report by DARPA and the US government that essentially came to the conclusion that machine translation is impossible. It's too hard. There were many jokes being made, like what was the famous joke? The spirit is willing, but the flesh is weak. Have you heard this joke before? The spirit is willing, but the flesh is weak. And the joke was, what's that?
I think it's a part of the Bible.
Yes, it's part of the Bible, exactly. And it means, you know, that our nature is weak and we strive to be better people, but we are failing people. And so it comes from the Bible, the spirit is willing, but the flesh is weak. But allegedly, in those first days, it's a story that turns out not to be true, but it was a story in the New Yorker that suggested, you know, at the time people were interested in translating into Russian because of the Cold War. And so they had to translate, they claimed that there was a translation into Russian and back from Russian into German, into English. And the translation that came back was, the vodka is good, but the meat is rotten. Out of the spirit is willing, but the flesh is weak. So you see the semantic ambiguity in language. Spirit can be alcohol, but it can also be the spirit. The meat and flesh are different things. They have a philosophical meaning as well as a physical meaning. And so we need to know what the context is. And in many of the things that you heard in this lecture already, context is one of those important things that we need to integrate to make that happen. Now, back in the 70s, there was no way we could do this. AI was not at a state where it could create or use all this particular contextual information to do a reasonable job. And as a student, when I proposed to my advisor at the time, I don't want to just be doing synthesis, but I want to build a machine that I can speak into and it translates into another language and have it come out on the other end. Now, in the 1970s, this was crazy. And he was luckily very polite and didn't take my dream, but simply said, oh, go back to your office and work on your current project. But the dream stayed with me, and I later decided to come to Carnegie Mellon to work on one of these other boxes that we needed, Namely, in order to build speech translator, we have to do speech recognition, converting spoken speech into text, then converting text from one language to the other, and then synthesizing that text in the other language as audible speech. If we want to have a dialogue, we need to have this all in reverse, the speech recognition in the other language, translation into our language, and synthesis in our language. Now, in the 70s, we didn't have any of this. We only had this text-to-speech beginning to work that, as I explained, we had a reading machine that Stephen Hawkins could use, but by and large, all these other things were still an open question. And of course, all of this is a huge problem that interests us in Europe because we have many languages, and again, there are 7,000 of them. So we set out to develop this. I mean, I went to Carnegie Mellon to work on speech recognition. Machine translation was considered impossible. And so we worked at Carnegie Mellon. There was a team that was working on the first DARPA project on speech recognition, continuous speech recognition in the 70s. And so I joined this team to learn more about speech recognition, how to convert spoken speech into text. And I found out that these other boxes are actually much harder than the synthesis box because it has much, much more ambiguity, right? Because if you synthesize something, all you have to do is produce one waveform that is understandable. But when you have speech recognition, you can have many, many different waveforms that you need to map onto one text, which is a harder problem. Now, overall, this whole problem of speech translation then turned into a work with many stages. We developed consecutive, simultaneous, and language transparent systems. We started in 1991 at Carnegie Mellon when finally interest in machine translation also came back. People saw the possibility of actually building speech recognition, text translation systems, and we had first systems on speech recognition. So we had a first prototype in 1991 that actually worked, but it was very small vocabulary and it was restricted syntax and so on. So in 1991, we had this first success of a first video conference in a limited dialogue, but it wasn't really practical. And then 20 years and 10 companies later, we finally had a product where on a phone we could deliver full unrestricted speech translation from one language to the other. As you see here in 2009, it was the first product where actually a speech translator was available on the phone. And we called it Jibigo. It was sold through the App Store. The App Store was also very new at the time. Apple came out with its App Store. It was very helpful for us. And the iPhone now had also sufficient computing power that we could pack all of this on a phone to create a full speech translation dialogue in 40,000 word vocabularies and 15 languages. And we had a startup company called Jibigo that built these and distributed with great success. There were many successful commercials that Apple ran with this app, and we also did humanitarian deployments with it that we still do. I don't have the don't have the slide, but this company was acquired then by Facebook. That's why you can't see it anymore on the App Store. Facebook bought the company in 2013, and again there were many ex-students from Karlsruhe in our startup company. And they're now still working, many of them still working in Menlo Park in California in the Facebook AI team and in the product team there. Building machine translation for posts, but also speech recognition for news and so on. We continued doing humanitarian deployments in 2009, after 2009, with the app, even though the company was acquired. We continue this type of work. We're still doing it in Karlsruhe. We have a project, Relator, which is funded by the German ministry to help translation for traumatized people from wars. So we do Arabic to German, German to Arabic, and now Ukrainian to German, German to Ukrainian. And there's an Institut für seelische Gesundheit in Mannheim, which treats people from those war regions. And so our translator provides the translation between those. So it's an app on an iPad. So you speak into it and the other person can respond in their language, and it facilitates a dialogue between these people. Now, what this all is considered, or what we call this, is consecutive translation, right? Consecutive translation, you say a sentence and it translates it into the other language, and you can hear it and the other person can respond. That's, of course, a little bit slower. So we wanted to go to the next step, which is so-called simultaneous translation. That is what we need for a lecture like this one, right? You all have heard about the lecture translator, right? Who does not know what the lecture translator is? So you all know. We're very proud of that. Thank you for not raising your hand at this point, because you should know this as a KIT student. It's something we invented. KIT was really the first university in the world that delivered automatic simultaneous translation via an automatic simultaneous recognition translation mechanism, and to provide subtitles that you can see on your laptop or on your iPhone. We're still working on that, improving it. But we rolled this out, and we had a first demonstration of that in 2005 to just show the feasibility. It was a press conference we ran at Carnegie Mellon and here in Karlsruhe. And since 2012, we actually offer it as a service at the university. So the idea is any professor here can put on a microphone, run this on our server, and get an automatic translation on a laptop, as you can see here, almost like subtitles while you're listening to the lecture. Now that too raised interest. We again saw ourselves in need of a startup company, just like Jibigo before, with a humanitarian or with the traveler translations. In consecutive translation, we needed it on a phone so that people could take it on travel. And after the acquisition by Facebook, we decided we needed to go to the next step to create a simultaneous translation technology so that you can get the translation as the speaker speaks. For humans, that is an extremely hard task, because the human interpreter has to listen to the speech, think about how to translate it, and then speak out that sentence in another language while listening to the next sentence, right? Because there is a delay. You have to listen to a sentence, and once you understood the sentence, you can speak it out in the other language as an interpreter. But your brain has to process the next sentence already. So it's extremely challenging for a human being, because you have to multitask this interpretation process. So it's very stressful. Human interpreters can only work 15, 20 minutes in a row, and then they actually have another colleague taking over to do this type of interpretation, because it is so stressful. Now, for us as machines don't have that limitation. We can put 5 computers in there, one that listens to the last sentence and the other one to the next. We don't do it this way, but we can create this without these machines being tired, and they can work continuously. Our challenge, however, is to do that at low latency. In the consecutive translation, you have to wait until the sentence is finished, and then you translate. We cannot afford doing that in simultaneous translation. Otherwise, you could only listen to the translation after the end of the lecture, and it's not useful for simultaneous interpretation. So we need something with low latency, which means we have to output words before the sentence has even finished, and that creates an additional prediction task for the AI to really know what comes next and what you should be saying in the next word. Just to give you an example, in German, for example, if I say, who does not know German here? You all know a little bit, I hope. So you know the word vorschlagen, to propose, right? So if you propose a date with someone, then you don't say, ich vorschlage einen Termin in German, but you say, ich schlage einen Termin vor. Now in German, you can say, ich schlage einen Termin für nächsten Mittwoch zum Thema neuronale Netze in der künstlichen Intelligenz, die in der Vorlesung von Herrn Weibel besprochen wurde. Und ich möchte da meine Forschung diskutieren vor, right? So you have this prefix for, which comes minutes later at the end of the sentence, and you hate it as a foreigner because you say, you know, if he starts with ich schlage, schlagen to beat somebody, right? So you don't want to translate the word schlagen with beating when you know it's going to be about a date, and the date is related to proposing a date, etc. So how do we do this? We know the context. we know the reasonableness of the expression. And so we know what is sensible to be translating. And if I say, ich schlage einen Termin, you know already it's going to be proposed and not beating someone up, most likely. Not always are we correct, but what our system does as a result is it predicts things and outputs them. And once in a while, as you can see in the lecture translator when you run, once in a while it realizes, oops, I made a mistake. And then given that we're producing text, we can revise the text and correct it, even with a little bit of delay. Happens very rarely, and that's why we can get away with it by a revision process. For humans, it's much harder. A human already spoke that wrong sentence and now has to take it back and then say, oh, no, I didn't mean it this way, I meant it that way. And that's, of course, much harder. Now, this all became clear in the European Parliament. The European Parliament runs one of the largest human interpretation operations in the world. They have interpreters in 23 languages, interpreting in all the other languages. On occasion, they have to go to what we call a pivot language, namely they go to something like English, and somebody else translates from English into Maltese, for example. So it's a very complex task. Now, nevertheless, it's of huge cost to do that. They have these interpreters for all these languages, and they spend, this is a number I have from 10 or 20 years ago. I'm sure it's much more expensive, but at the time it was 300 million euros a year. I'm sure it's doubled at least in cost right now to have all these interpreters doing it. In addition, they have a translation department that translates all the text. So the agendas, if you go to the European Parliament, they have stacks of agendas that have been translated into 23 languages. Enormous expense. And so the Secretary General of the European Parliament at the time approached us and says, can we try out your system for an automatic interpretation? So we did that. Don't want to cover the face of the, yeah. So this is us in 2018, when we did the first interpreted conference at the European Parliament that was automatically interpreted. It was wonderful because it made us friends. So we first were, of course, worried we would be hated by the interpreters. All of these interpreters, of course, initially are fearing for their jobs, but it turned out it developed into a good relationship because we explained to them the limitations of the technology, and they could see the limitations, while they could see the advantages of the technology, namely that we can build systems that can interpret from one language to the other when the interpreter is not available, or when the interpreter, the human interpreter, doesn't want to do it. Do they sometimes not want to do it? Sure. For example, voting sessions, when they just read out the votes, are extremely boring for humans to translate because it's just reading the numbers of the voting results, while at the same time it's very stressful because you can't get the voting numbers incorrect. I mean, if you make mistakes, it can be an international incident. So it has to be correct, while at the same time extremely boring. So in those situations, we were welcomed, and they really wanted to see this happening. Now the pandemic came along. We had everybody went online. We couldn't deliver lectures in person anymore. So for the Parliament, we started this company. It was called Kites, and the company developed these simultaneous interpretation systems for universities and for the Parliament. But as I said, in 2020 or 2019, we had the start of the pandemic, and we couldn't have lectures anymore. So we started doing everything over Zoom like we're doing now. But we wanted to have our translation technology or the translation service running at the same time. So people had to run with two different screens on their laptops. And so we said, well, why don't we approach Zoom? Everybody was using Zoom. Can we get an API so we can do the translation inside of the Zoom call? And a dialogue ensued. And so that company was then also acquired by Zoom at the time. And if you now run Zoom with subtitles and translation, it comes from our team. They're all sitting in the Höpfner building. There's a large team of 20, 30 people now doing research for Zoom to advance the speech recognition and translation technologies in this kind of communication scenario. So that's, once again, something where we went from some very fundamental research to get the speech recognition, translation, and so on run really well in low latency. And I'll talk about the technology in the moment. And we pushed it all the way to something that actually is now in common use. Here's a picture of me talking, and it does the subtitles, and you can get the transcript of the talk. And you can do this by yourself when you just open Zoom and click on the CC, the closed captioning thing that comes from our team, right? Große Freude, dass ich heute bei Ihnen sein darf und Ihnen ein wenig über unsere Forschung zu. So you know how this works. Now, the next thing that we're worried about, and always were, was the question that speech and language is not only textual. When you get these subtitles, of course, you get subtitles underneath the screen, and that's text. Now you need to read the text while you're listening to the speech or while the speech is going on. But we know from humans that our human interaction is not only textual, it's not only speech, but it's multimodal. We have gestures, we read lips, we look at each other's eyes, we touch, and so on. All of this is a multimodal communication that delivers for us as humans redundancy and robustness. And so we need to involve that too. So we worked on this also over the years. We had various projects in the 90s and 2000s where we looked at lip reading, handwriting recognition, subtitles on I took this picture in China. For those of you who read Chinese, I cannot read it, but I found out later that this means no entry for tourists. Of course, when you're tourists here, you cannot read the sign. I thought this was funny, but we built a system, a product that could actually translate this from a camera and so on. So can we do this by multimodal information? Can we show or point? This was in fact our first product in that direction in 2001. We demonstrated this, a system that could take a camera picture of a Chinese sign and give you the translation in English. That continued, and again, the company did some stuff and so forth, and later Google, there's many stories on that too. Google started to do something similar, and now you have this something like that on Google Translate. We also worked on multimodal things where we had heads-up displays in goggles where you can see the translation. We proposed that in 2005, and in Google Glass and other applications that is now being pursued as well. And we started with this whole notion of language transparency instead of just speech translation, because we don't want to only translate something in another text, but we want to make the whole experience language transparent. So this is, again, videos from many of our research projects over the years. This is work from Rainer Stiefelhagen. He did his PhD thesis on this topic of focus of attention tracking. And as you can see in some of the earlier projects, we showed that we can in fact track the focus of attention. That's important in meetings, right? If you want to translate something, if I say to you, let's see, what does that mean? And I point at your t-shirt. Now you know that I'm talking about your t-shirt. But if I say, what does that mean? Then you know I'm not talking about his t-shirt, but something else. So you need to know focus of attention. What am I focused on? What am I pointing on, right? So to understand this in an open meeting situation, we need to understand the communication act or Kommunikationsakt, as we call it, the meaning of a particular interaction in an open environment. Much harder problem than only the translation things that I discussed so far. And so we started tracking people, doing focus of attention tracking. As I said, there are now several groups. Rainer Stiefelhagen now is a professor here, and they are doing this work for the Institute for Sehbehinderte. And we still collaborate. We're doing some of this in our own lab to have pointing gestures and so on. The other thing is we developed emotional speech recognition.
Go to sleep now. Go to sleep now. Go to sleep now. Go to sleep now.
An example of the first emotion recognition from speech. So we can determine the emotion from the speech and from what somebody's saying, also facial expression and so on. And again, this was work that then went into various applications where we can use the emotion. That, again, depending on your emotion, the translation and the meaning of a sentence changes substantially. What we're doing now is yet another interesting project or an interesting idea, which is this idea of dubbing. So we have a team now at our lab. Dubbing is sort of the next frontier for us, where we're saying if you watch a video, very often you get subtitles, right, in the other language, right? But in Germany, very often the movies are dubbed into German, right? So you watch an American movie, but the actors are speaking German, right? Well, the actor doesn't speak German. The actor spoke English in the movie, but what they do in dubbing is they hire a voice actor, and the voice actor now has to get the translation of that sentence into German, and they have to try to speak the German sentence in exactly the same time that the English that the person speaks in English, the English sentence. You know what I'm talking about, right? You all watch American movies in English. And so you have the German speech sort of done at the same time as the English actor is speaking, but very often the lips don't match, and you see that the lips and the voice don't match. And of course, the voice is not the voice of the original actor, it's just the voice of the voice talent that is doing the dubbing, right? And so, of course, Germans get used to the German dubbed voice, but it's not the original one. And I particularly, in some movies, I think it's terrible. Like, for example, Arnold Schwarzenegger dubbed into German is awful because it's just more funny when you hear Arnold Schwarzenegger in English speaking with an Austrian accent, etc., etc. So wouldn't it be much nicer if we did that? And of course, there's also business reason why you want to do this. You want to get translation into many languages, dubbed into many languages automatically. Can we do that? So we're working on a system now, both in research as well as in startup company, where we're looking at the entire chain of dubbing, meaning we have to take the voice, recognize the speech, translate it into another language, do the speech synthesis in the other language. Then the speech synthesis doesn't sound like the original speaker anymore. That means we have to do voice conversion in the target language to the voice of the original speaker, so it sounds like that speaker. And then we have to manipulate the lips so that the lips move like the translated speech and not like the original speech. Understood all the steps? So we're translating automatically, we're doing voice conversion, and we're doing lip manipulation. So this is an example of one of my cognitive systems lecture that I gave during the pandemic, 2022.
Ganz herzlich wieder zu unserer Vorlesung Kognitive Systeme. Wir fangen heute ja mit dem tatsächlichen Stoff an. Super, dann begrüße ich Sie ganz herzlich wieder zu unserer Vorlesung. Super, then I warmly welcome you again to our lecture on cognitive systems. We are starting today with the actual substance. I would like to apologize for the delay of a few minutes. We still ではまた認知システムの講義に皆さんをお招きします。今日から実際の実態から始めます。数分遅れて申し訳ありません。マイク
Find the pattern and all. So
Super then. では
sorry. This is the president of Carnegie Mellon.
21, a Smart City Institute, which has become a campus-wide initiative that encompasses so much of our work at the intersection of
21. Ein Smart City Institute, das zu einer Campus-wide Initiative geworden ist, die so viel unserer Arbeit an der Schnittstelle von Technologie und Gesellschaft heute umfasst, ist eine Feier einer harten Arbeit. 21. スマートシティ研究所はキャンパス、 ホワイト、イニシアチブとなりテクノロジーと社会の交差点における我々の仕事。
And that we actually have practical solutions already that are usable in actual dubbing. And we're beginning to work. In fact, I just started collaboration with Warner Brothers, which is one of the largest media companies in the United States, and with various other instructional video companies and YouTube. There are many interesting applications, and of course, still many scientific issues and problems that need to be addressed. Titanic. Why is Titanic here suddenly? I don't know who knows about the Titanic story. You know about this submarine that imploded, right? A year ago. Well, I was in that submarine 2 dives before it imploded. And we did an experiment where we used exactly this voice dubbing technology to improve communication technology. Here's that dive that I was on in 2022. So it was 2 dives before the implosion. Here's what we did is we all put microphones on, and we built a laptop here in our lab at Karlsruhe to do the automatic recognition of what we say in the submarine. One of the problems is underwater, you cannot do a radio transmission because of the salt water. So one of the problems that submarines have is they do the transmission via sonar, and so sonar is very low bandwidth. So the only thing communication that was available was texting. And texting at 4,000 meters is complicated, and somebody has to pay attention and all. And it's a critical communication tool to communicate with the ship. And so we developed a system where we recognize the speech, convert it into text, send the text via sonar to the surface, and at the surface, one of our graduate students, Christian Huber, who's working on his PhD in our lab here, was at the surface on the ship, running the program that converted the text back into speech and the video of me speaking that sentence. So here's Christian Huber on top of the ship with the laptop that does the generation. And
Hello, I am Stockton Rush, CEO of Ocean Data. On our research mission, we are planning a deep dive to the legendary wreck of the Titanic.
I am Alex Weibel. We are excited to be part of this mission. Our role is to contribute to better communication between the submarine and the ship on the surface. Such communication is crucial. Unfortunately, normal radio transmission does not work deep under the sea. That is why we are planning to try a different approach. We are recognizing
sadly, of course, this tragedy happened just last year, so we cannot continue this research. Very sad. I was just last week meeting with some of the explorers that survived this tragedy, and everyone is, of course, heartbroken because it's exploration, and exploration always has risks. You see, there are many of these modern tech marvels that are not well tested out that are in that category. But we do some interesting similar things. This is an experiment where we do dubbing with a lady here in Germany who has a speech problem that was caused by a virus. And
ausgebildete Juristin, aber wie bei der KKS kann ich leider nicht mehr gut sprechen.
I am a graduated lawyer, but unfortunately I cannot speak well anymore due to my illness. But I hope that I can communicate better with other people again with the help of new technologies.
her voice not only into another language, but recreate her voice and restore the speech patterns that are understandable and intelligible. And we have obviously we enjoy doing this project because we can really alter someone's life in a positive way. And so this is an ongoing effort that we're doing. We're now down to 10% error rate. We had initially 16% error rate on the speech. And so it's getting to now in the realm of where it's actually useful for her. Okay, I talked a lot about all of these applications. Let me go through the technology, since this is a neural network course. Why neural networks? Why tell you all these stories in neural networks? Because the fundamental research in neural networks was crucial in all of these achievements. And so by us pushing to build these practical systems, we were challenged to solve really, really hard AI problems that were not possible in the 70s or 80s. And so it is a journey over many, many years where we worked on solutions and approaches that would make that possible so that we can reach this final goal as we are now reaching it. So the problem that I mentioned with the ambiguity is that first challenge, namely that anything that you say is ambiguous. If I say, give me a new display, it could be, give me a new display. Time flies like an arrow, but fruit flies like a banana. So you have different interpretations of any sentence. Spirit is willing, but the flesh is weak. Vodka is good, but the meat is rotten. If the baby does not like the milk, boil it. Do you mean the milk or the baby? And depending on which your interpretation is, the translation would be different. In German, for example, you would say, wenn das Baby die Milch nicht mag, koche sie oder koche es, right? And we hope that we mean koche sie, the milk, and not the baby. But how do you know? How does the AI know? It must have a lot of contextual information that you don't cook babies, but that you cook milk, and maybe the context of the conversation. So we got three challenges: uncertainty, multimodality, that we need to have multiple modalities at the input, and we need to be learning. Now, AI is not a new field. AI started in the 1955. I was just privileged. A couple of weeks ago, I gave a lecture at the Carnegie Mellon presidential meeting in Silicon Valley. And after the talk, Edward Feigenbaum comes up to me. And Edward Feigenbaum is the only remaining member of the original AI conference at Dartmouth in 1955. He's an elderly gentleman now. And it was wonderful to see him. In that original conference, there were a couple of famous professors that defined the field under the guidance of DARPA. And it was McCarthy, Minsky, Newell, and Simon. Herbert Simon was a Nobel laureate. He was on my thesis committee at Carnegie Mellon. He did the work on original AI, and Alan Newell, also at Carnegie Mellon. They were all colleagues that are now passed away, but they defined the original field. Now, AI as a field had many booms and busts. People got excited. I have old Time magazines of 1979 or so, where people said computers and robots are taking over in 1979. Of course, none of that happened, right? The machines were pretty dumb, and the robots never happened. The technology was too limited. And the question is, why was that? And are we maybe again in some boom or bust cycle? Well, at the time, people didn't have the approaches we have now. There was logic was used as one approach. Rules, that was the common approach in the 70s and 80s. People tried to put everything by rule. Speech recognition by rule. Machine translation by rule. That means you have to write rules for every little phenomenon in the world in order to properly translate it, the syntax, the semantics, the meaning of different words, the context, etc. I mean, I was a graduate student at the time, and I said, that's lunatic. This will never happen like this. It is impossible to build AI by being forced to having all these rules. And even if you could, they constantly change. The world is always changing, and the world is not logical either. Search was another approach, but as you know from Go or chess, to search through all the possible moves is impossible. You cannot search all possible moves in the space, even with chess. And so what you need to do is you have to have in chess programs, for example, you have an evaluation function. And the evaluation function is an AI, it's a pattern recognition. The pattern recognition, a human chess player sees a pattern and knows from his or her experience that this is a good move or not a good move. And so experienced chess player do pattern recognition at some point and not search. Now, how do you do this pattern recognition? Clearly not by rules, so we must have machine learning. So for me as a graduate student, I listened to all these famous professors talking about search and rules and logic, and I shook my head and says, how can you possibly think that AI is solvable without having machine learning? And so we started working in secret on machine learning solutions to this with some of my colleagues. And there are statistical machine learning methods. But one of the things I was drawn to certainly was brain style computation. And it comes from the simple observation that you say, how does the brain do these things? I mean, we have no trouble recognizing a face, but we can compute the square root of 3,260.55 in our head. Impossible, right? So is a pocket calculator more intelligent than a human because it calculates a square root faster? We would all say no. But, pocket calculator can recognize a face. So how is this brain style computation different from traditional von Neumann machines so that we can do that? And the answer is, of course, parallel computation, that we have many small processors we call neurons in our brain that are heavily interconnected. And this joint processing, and each of these processors is actually very inaccurate and not very good. And they die all the time. Every time you do like this, you killed 100 neurons, right? I just killed 100 neurons. But the thing is, it works. It's so redundant and it is so readjustable and adaptable that we can do this with billions of neurons and compute interesting hard problems like speech recognition, machine translation, vision, and so on. And when you look carefully, it is this interplay of many parallel processes that work together. Now, in this case, programming is clearly impossible, right? Because we have to have machine learning to adjust each of these neurons. Now, that was not a new discovery and a new idea. In the early 60s, there was already an attempt, so-called perceptrons, which did you study perceptrons in the course? So you know what a perceptron is, and you know what its weakness is. Its weakness is clearly performance because we cannot. We still have half an hour, right? Oh, no worries. Just wanted to make sure I'm not out of time. So perceptrons, are first neurons. And during my PhD thesis, I thought this is really the way to go. We need to have these processors that can be combined with many other processors to solve problems. But perceptrons are just a linear machine. Now, this was understood already in the 60s when people worked on them, but they couldn't compute them, right? I mean, it wasn't so hard to see how you would stack. In fact, there's a book by Niels Nielsen, Stanford professor, who came out in the 60s or 70s, where they talked about perceptrons, and they said, well, what we would really need is stacking those neurons into multi-layered machines. Then we could do it, except you now need an algorithm that trains them jointly as opposed to independently from each other. So all the efforts in the 70s failed in a way. There was also neocognitron, which is arguably a convolutional architecture in the 70s by Fukushima, that had interesting combinations of multi-layered machines. But the problem with all these approaches was the neurons have to be trained independently. And if they're trained independently, they can't work together in a jointly optimized fashion. Backpropagation came around, and backpropagation was a solution because now we can train multi-layered machines without having to specify what the hidden neurons have to do. And you know how that works. You've learned this. Now, backpropagation was 1980s or later, and so-called Boltzmann machines, another approach that does multi-layered machines. And here we could look at fusion and look at representation shift invariance. I'll talk about this a little bit. And then if we do more, then we can do deep networks. And this is today's challenge. And then finally, AI. Now, why neural networks? Many things are too complex to program. Machine translation, different meanings, automatic recognition, different meanings. But more interestingly, and in fact, when I started then in the 80s with back propagation, there were two interesting things to me and one problematic thing. The problematic thing is if you have a pattern classifier and you put this on a pattern, you need to do segmentation first, right? You need to know where is the pattern before I can classify. And that's of course a problem because segmentation is inherently also a pattern recognition problem that makes errors. So you have two errorful processes. One is finding the pattern and the other one is classifying the pattern. And we said, no, we need shift invariant classifiers. And I'll say a word about this. The other thing though is in those days, there were also neural network, non-linear classifiers that were much simpler. So we had a lot of problems, I would say, when we started the work on neural networks in the late 80s and 90s. There was a gentleman at DARPA who hated neural networks. There were many who didn't like neural networks. People called us neural nuts because they thought it was some kind of a cult and people who just had crazy dreams. The method of the day was rule-based and maybe statistical learning, but there was neural networks. And so I had discussions, and at DARPA they say, well, a k-nearest neighbor. Do you all know what a k-nearest neighbor class? Who does not know what a k-nearest neighbor classifier is? Okay, do you all know? A k-nearest neighbor classifier is a nonlinear classifier, right? It can create arbitrary decision circuits. Why do we need neural networks? A k-nearest neighbor can do it, and it's much simpler, easier to compute, and so forth. One of my arguments to, and this was an argument proposed by people at DARPA. We had arguments with people at our research labs and so forth. Why do we do these complicated neural nets when you can do it with a much simpler technique, non-linear, just if you're only interested in performance? My answer to them was twofold. One is representation. In the neural network, if I get a good classifier, it builds hidden representations that I never specify. And these hidden representations in the hidden layers are not only useful to get nonlinear classification, they are actually knowledge discovery that is happening inside of a neural network. At the time, we demonstrated this. I'll show you the pictures, but people argued still, etc. It took another 20 years for people to discover. And if you look today, the knowledge representation that goes on inside a neural network is everything, right? OpenAI, large language models, it's not necessarily just the word you predict. It's the discovery of all that knowledge that it can combine them in very interesting ways that seem like magic. It seems like it's intelligent because it can produce things you haven't predicted like this, right? And it comes from these powerful representations. Second thing is merging representation. It doesn't really matter whether this is speech, text, vision, characters. It's just feature, right? You know that one, right? We traditionally have had vision groups and speech groups and this group and that group, and they will do independent things. Nowadays, it's just another vector. For your neural networks, you can feed it speech vectors and vision vectors and so on. And we understood that in 1989 and started working on multimodal neural networks since then, and could show that these actually generate very powerful methods. This picture here is, of course, word2vec, where you have semantic representations that emerge from neural networks, where you can actually see that words in a particular multidimensional space come close if they have a close semantic meaning. And we exploit this kind of properties in many interesting ways, and I will show you in a moment. Now, the question is, who invented all this? You know, there are, of course, celebrated people who win awards, etc. As it turns out, they didn't invent it. So I recommend for you, if you really wanted to interested to see where these ideas come from. Many of them are much older than people think. It's not happened just by deep learning in the last 5 years. Some of the theoretical work really goes back to 60s and 70s and 80s. And so to trace that back is important for academic honesty. And Jürgen Schmidhuber in Switzerland, he's now I'm not sure. He has an interesting blog you can read where he in fact shows how many of these methods trace back. I highly recommend it if you're interested in the historic sources for all of this. And they show that backpropagation was actually developed much earlier. Convolutional neural networks, arguably, we did that, and recurrent neural networks, other people that no one remembers. Let me talk about the one that we did, which is shift invariance. As I said, segmentation is a problem. You don't know where something happens. If I want to recognize this pattern as to be the same, you need to know that it's just a shifted version of that pattern. And so you need if I just plop down a multi-layer perceptron or any classifier on top of both of these patterns, they're different patterns, right? Yes? You see that they're different patterns. If you just look at the bitmap, right? So classifier get confused by that, right? Your eye does not get confused by it because you know it's the same pattern just shifted, right? So how do we teach the neural network to ignore the shift but recognize the pattern? And the answer is to build a neural network that does shift invariance. So we proposed that in 1987. You can see these early papers, 1987, 88, and 89, where we applied that to speech patterns, because in speech you have that situation, speech flows by, and you want to recognize when a phoneme occurs or when a particular feature occurs independently of the precise positioning. If I need to do segmentation first, I will have a higher error rate, right? So we need shift invariant classification. And so we did that. I hope you have already discussed that. You had that in class already? TDNNs and convolutional neural networks. So what they do is they have essentially a pattern that shift through and create patterns in the next layer. And again, in the next layer, you have patterns that shift through, and eventually you make a decision. Now, how do you remove the position dependency of such a classifier? Is you take the shifted gradients that you do by backpropagation and you share their weights. You link their weights to make sure that a shifted version of the same feature cannot have a different gradient. So that's why you during backpropagation training, you link those weights and you merge them together. You slave them to each other. And if your training is forced to ignore the shift dependence or position dependence by this trick, then you get actually shift invariant, shift independent classifiers that work extremely well. There's a demo. Do you still use a demo page, or?
I'm
The,
not too sure.
Okay, so if you want to try that out at home, there's a demo in this website where you can train a shift invariant classifier with a time delayed neural network, and you can train it also with a standard backpropagation, and you will see that the standard backpropagation will not train those patterns correctly. And if you have a shift invariant time delayed neural network architecture, it learns these patterns quite robustly. So it's lecture demo ear.kit.edu. But I will not show this now, but it just learns it, yeah? Let me go to the next one. So we could demonstrate this in the papers in 87 and 88, but if you have the pattern in speech that are shifted from left to right, you still get the correct classification at the output. Now, here's the more interesting thing. So we achieved shift invariance, but then the question is, what did these neural networks learn internally? And so we could look at the activation patterns. And again, in those days, those networks were tiny. We had like eight neurons in this first layer. It's ridiculous in today's world. But it was in some sense nice because we could actually see and interpret what these neural networks learned and really see that they did learn abstractions that we had never told them. So we learned, for example, that this hidden unit number 3 learned a certain weight pattern that had a decaying energy. As you can see, we see the pointers here. And if you have these decaying energies, if you ask a linguist or acoustic phonetician, they will tell you, yes, I know what these decaying energy patterns means, these trajectories. These are trajectories in the resonant frequency space of the vocal tract, and we call them formats. These are resonant frequencies in the vocal tract movement as you move the articulators. So as we speak, our articulators move, and the spectra have certain changes in the spectrogram. And these changes are learned by human beings. And we know that we can give these patterns to humans to listen to, and they will hear ah or oo or da or do, etc. So we see that these neural networks, without us telling it, learn acoustic phonetic features that linguists have studied for decades. Very exciting, because we never told that they had to do that. So with that in mind, we then also looked at transfer learning. So if you take the hidden units from one network and the hidden units from another, we can combine them. So if we really can learn abstractions in the hidden representations of a neural network, we should be able to reuse them. And that is so true today in many, many practical ways, as I will show you. Namely, that if I learn something in one task, I can maybe learn that hidden knowledge, use that hidden knowledge for something else. So when you're playing with Legos or with blocks as a child, you learn motor activity with your hands, you learn to recognize objects, and then later in life, you don't play with Legos anymore, you don't play with blocks anymore, but you drive a car. You don't have to relearn your visual perception. You don't have to relearn how to move something, because you learn those behaviors on a different task. It's hidden representations you learn, but you reuse them for a different task. We do this massively today. We train all these networks, all the pre-training we do today, all the, you learned about word-to-vec and, wave-to-vec, etc. All the things you do right now, it's almost a commodity. You have these representations trained by large language models, and what we now do is we adapt them to a particular task, but we use them almost off the shelf as a commodity to build larger systems. And it's only because of this power of hidden representations that can be reused. We build larger networks by using additional glue units that let you merge separate hidden representations, build larger networks, etc. That worked astonishingly well, even though we didn't train the entire thing. We built it from modules. And eventually, over many years, we were able to show that that worked fine with much more data and much more connections and so on. We also had two-dimensional, shift invariance in one dimension was necessary for speech. But if you have different speakers, also the patterns shift in frequency. So we proposed two-dimensional shift invariant patterns, and that was published in 1990. And then eventually, of course, the vision community saw that if you can do two-dimensional patterns, then we can use that also for vision tasks where we also don't know exactly the precise positioning. And that's where then handwriting recognition was applied, and you can apply it to road sign detection and so on. And so the history of it is that it then turned into an approach that people also used in vision. And as a historic accident of time, people didn't like the term time delay, because time is more something you do in speech. And for the vision researchers, time delay doesn't really make sense. So they started calling it convolutional neural networks, but they knew it was TDNNs. So if you look at the paper by Leclerc and company in 1989, gradient-based learning applied to document processing, famous paper. If you look at the text and at the reference, you find that TDNNs are demonstrated and shown and explained as a precursor of the convolutional neural network. That they are the convolutional neural networks applied to speech, or phrased other way around. Speech invented it, and then it was actually used in vision. So it's important, you should know where it actually comes from. So today, backpropagation and convolutional neural network and recurrent neural networks are celebrated as certain people, but they didn't invent it. It came from different origins. As it turns out, the word convolution is not even novel. It turns out that what you do in a convolutional network is actually not a convolution, it's a correlation. But the weights are trained, so who knows what it is. The word convolution, actually, I found this out 3 weeks ago. I had a conversation with an old colleague at the University of Washington. We had coffee together, and we talked about the fact that convolutional networks are really tunneling networks. He knows that, and he agreed. But then he talked about the paper that he wrote in '87, where he, as an electrical engineer, talked about convolutions and neural networks with convolutions. And he remembers that Jan LeCun came back and they shook hands, and then he went off and started calling this network convolutional network and never cited the man. And so once again, it's a sad instance because he provided the name convolutional networks that was then applied to the TDNNs and became what we now know as these large CNNs. Now here's an example of
MEYER KOSSMANN STEMPEL FRANZ
again, the rest is history. Recurrent neural networks, that's also is an old idea. We did these, in my work, I did these handling neural networks, shift invariant things, but we were, of course, knowledgeable of the fact that if you need sequence processing, you have sequential applications, like syntax, words in sequence. And so we, in the 80s, 90s, came across a paper by Mikulainen and Dyer. Again, Mikulainen, nobody cites Mikulainen, but in my view, he was the first to use recurrent neural networks for dialect processing. And I was quite intrigued with his work. Forgotten, nobody remembers him, but we had a first paper where we picked up that idea from his work and applied it to connections modeling of dialogue processing at ICASP 91. And then we extended it to machine translation, Wang and Weibel in ICNN 95, where we did connections transfer and machine translation. But we had these networks so painfully small that we couldn't do it just with words. We had to create linguistic structures that we would then transfer from one language to the other. Make a long story short, we hit the limits of our computation. And it was just simply too difficult to do this on the hardware of the day. And so we continued with statistical translation at the time, and then had some progress on statistical machine translation that worked well. That was, again, fairly, that was heresy in the 90s also, because people thought translation must include linguistics. You can't just machine learn it. Even statistical translation was something that people didn't believe in, but performance was then ultimately so much better that it really was adopted. Now, AI performance in 89 to 2010, most people did, we worked on these models, but it never really got the complete impact of it, because you could, with statistical learning and other learning methods, achieve comparable performance, but with much less computing requirements. So we could compute these with lesser effort. We always, for neural networks, had to use supercomputers and wait several weeks until they finish. And with some other approach, you could do that more quickly. So until 2010, the community largely ignored it. And that's also why we never really went beyond one hidden layer, because it was computationally infeasible. And the mathematicians told us that that one layer should be enough and that you should never need another layer. Never believe the mathematicians. They live in a world of their own, which makes assumptions that are impractical in many ways. And so computing eventually resolved this. As you know, NVIDIA, have you looked at the stock price of NVIDIA? Who has invested in NVIDIA? Oh! So NVIDIA, you probably made a lot of money. It went like in the last couple of years, 3,000%. I mean, I've never seen something like this and the analysts are saying it's not a bubble because they actually make that much more money. So it's actually a stock price that is justifiable, and people expect even further growth. This is in a few years, and maybe. Why? Because the whole world now suddenly knows that brain cell computation has arrived, it's working, it's never going to go back because the performance we're getting is just so much better, and all we need is more computation, just more. And so at our lab, we have one person dedicated to buying NVIDIA cards, because we can't get enough of them. And of course, if that's little us at the university institute, imagine what's going on at Microsoft and at Google and so on. They're just, it's a race for computing. So when that happened, more neurons, more layers, etc., we saw huge performance gains. Speech recognition, 30% better, machine translation performance. And I'll show you, here's a curve. We went from GMMs to DNNs, then CTC, then time delay neural networks and sequence-to-sequence models. All of these models produce enormous improvements on a DARPA challenge. It's a database that was introduced in 1993, and we were the best group in 1993, or one of the best groups in 1993, on that task that DARPA gave out with an error rate of 53%. So every second word was wrong. It was terrible, right? And so now we get human performance with neural networks. Here's the result. This happened in 2020. We had a press release. Elon Musk commented on it. AI in superhuman performance. We can do speech recognition on this difficult task that DARPA had produced in 93 at an error rate of 5%, which is, or better, which at low latency, which is what humans can do. And here's the error rate curve as a function of latency. So if you reduce the latency, eventually, of course, you need some context, but with a latency of 1 second, we reach human performance, which was a nice breakthrough. Machine translation, the same thing. We started with these neural nets and had to give up or couldn't continue. We went to statistical learning and went full circle back to neural learning on machine translation. Jan Nihus, I'm sure, has giving you a lot of details and lectures on machine translation. That's his specialty. And as you see, when we applied this to a WMT benchmark test, you see that the results really jumped in performance when people switched to neural machine translation. Nowadays, of course, it's transformers. Transformers are, again, multi-layer architectures that I'm sure you've studied, right? You have covered them already? Yeah. So, so they give another good performance. Anyway, so why are neural networks so interesting for machine translation? One phenomenal result that we had also in 1920 or so was the holy grail of interlingua. What is an interlingua? Linguists have postulated for many years that if we can build a representation of meaning between two languages, then I don't have to build a translator between each language. Let's say for the European community, we want to translate between all 23 languages, right? Then I have to produce 23 square many translators to go from each language to each language, right? Which is very expensive to do, both in terms of development time as well as software engineering. And so we had this dream already years ago to build an interlingual, but at the time it was done linguistically. People came up with an interlingual of meaning where you had to develop a semantic representation of the meaning of the sentence. Now, having a semantic representation of the meaning of the sentence means every possible meaning in the world is possible. So that's why our early systems were limited to a certain domain where you can then only do a hotel reservation or so, and then you have things like the day of the week and the time and so forth, a name, and you could do that. But general purpose, semantic representation that you can use as a middle point between any language was impossible. And if we try to do it, the performance was always worse than a direct translation between two languages. So the breakthrough came around, I think it was 2020. Do you remember what this was Lei's result? Lei did his PhD thesis here in our lab, and he was the first, and Google at the same time with so-called, in parallel, they came out at the same time, with so-called zero-shot translation. What does it mean? You train a system between German and English data, and English data, and English-French data, and then you can automatically, for free, get translation from German to French, even though I never trained it. In other words, my hidden representation of this translator has enough knowledge about the meaning of sentences that I can get cross combinations between languages for free. And the performance doesn't even suffer. And so this was Lei's breakthrough in his PhD thesis here in Karlsruhe, where he could show that such a quote unquote, it's not really an interlingual, but it is like an interlingual where it develops, where it creates that middle point. Now push this a little bit further. Again, it's a hidden representation of meaning. Does it have to be speech and text? No, we could have images. And now you see this, of course, OpenAI, many others do that now. You have representation that you train not only with speech or with text or speech or language, you train them with images too. So we can now do for free a translation between images and text to images with generative AI. So you get all the combinations of them in the same model. It's just super exciting what we can do there, and it's actually doing it. So I don't have time to go through all these things. We work on many different things at our lab. Summarization, accent conversion to convert, for example, a foreign accent to a local accent. I don't have time to show that to you, unfortunately. Come on, it's slow in switching. Oh no. Okay. Error correction. Speaker diarization, big problem if you have an open meeting, recognizing who's talking. Is it me talking, someone else talking, to put a label on the speaker. Adding new languages. So if we have a hidden representation of meaning, can we add another language that was not part of our original training? We're beginning to see good results with another PhD thesis that's currently ongoing. Very exciting, because without it, we can never do 7,000 languages. How do you use 7,000 languages? You would need the training data for 7,000 languages. Impossible. So our dream is to make that so a common representation in such a way that we can plug in additional languages by the communities themselves. If you have a small community in India or in Papua, can they add simply words or sentences and add it as a new language? And we hope that that is possible. Face dubbing continues. I show you what we are doing there, and we have different methods that add more quality. You see here, for example, much better quality in the synthesis, different resolution. Pointing gestures to use the pose and pointing in the recognition and conversion of dialogue. Verbalization of episodic memories for robots, some work going on to remember what did I do yesterday, to recall that, and so on. I'm over time. Let me just give you one more slide on something that I'm very excited about that we're also doing. We call that sleeping machines. What's the next generation in AI? What comes next? So most of these things we're doing now, right, in our research lab. But what will be the next thing? artificial general intelligence, right? So everybody talking about it, but nobody knows. An autonomous AI agent that can act like an assistant. We're getting quite interesting results now with all the things that, ChatGPT, GPT 4.0, for example. There's some really exciting things going on. We're working on some models in that direction. But one of the things I'm quite interested in is sleeping machine. You say, what the fuck? I mean, sleeping machines, what can that possibly mean? Well, I'll give you the one or two slides version. Intelligence is the ability to adapt to change. All of our systems right now require huge amounts of data, and they are backward looking. So your large language models use the data that has been collected so far to predict the future, but they don't adjust. You have to retrain the whole thing. Now, humans don't do that. And how do humans do this? Every day, we train on new test data, right? Every day we see and we hear something, and we train on that. So something new happens, and you screw up, and you don't know what it was, and you don't know how it worked. You're sitting in class, you're learning something, you don't know how it works, right? And we don't know how to deal with it. So we muddle along at that point. But then how do we convert that into new knowledge? That's lifetime learning. All of our life, we're adding new knowledge. And how does that work? Sleeping is a critical element of it. Why do we sleep? Animals could get eaten while they're sleeping. So from an evolutionary point of view, it's stupid to sleep because you waste time and you're vulnerable, right? But in the sleep cycles, important things happen in the brain. Namely, we have these different cycles, rapid eye movement cycles and non-rapid eye movement. And these rapid eye movement cycles cause us to dream. Yes? You all know what dreaming is, right? You all know the expression sleep over it, right? Mal drüber schlafen in German, right? Probably every language in the world, I don't know, in Chinese, is there an expression like that? Yes. So most people have an expression in every language to sleep over something. So the idea is you perform better after having slept over a problem. So how does that work? Our brain has emotional reactions to things that we didn't do well. And at night, we do data augmentation during the rapid eye movement. So during the rapid eye movement phase, we create artificial data to go through all kinds of phases. If you write down what you dreamed, you will find out that you're dreaming bizarre combinations, psychotic combinations of things that have preoccupied you in the days before. And so why do we do that? Because we create artificial augmentation data. And with that augmentation data, we create representations in our long-term memory. And anyway, I don't have enough time to tell you all this, but we're working on a number of ideas that give us possibility of, during the day, having a short-term experience where our system underperforms, modify it correctly, and then put it into a long-term training cycle that adapts the existing model to behave with the new knowledge. And that's what we consider sleeping machines, because it's machines that regenerate, that modify during a lifelong learning cycle that we believe is the way forward for AI, so that they can become more personalized, not generic, and that they become more dynamic over time, learning additional knowledge. So now I switch to patients. Thank you so much for giving me the opportunity to speak to you. I hope you found this a little crazy but interesting. We still do a lot of research coming in here. Colleague Janihus, I think is doing a wonderful job in taking this class, but come talk to me if you're interested in interact with some research projects. We're always interested to speak with you. Anyway, thanks.